Today we will complete our discussion on linear independence and then go on to basic theory of systems of first order, linear ODEs. So last time we gave the definition for linear independence of sets of functions. Let's have an example. Start off with an example today. Let's show that the set of functions e to the t, e to the minus t, and 1 is linearly independent. Linearly independent on R. So we want to show that these functions are linearly independent on R. So here's one solution. Suppose that C1 e to the t plus C2 e to the minus t plus C3 is equal to 0 for all t. So then we want to show that necessarily C1, C2 and C3 are all 0. Okay, so if this equation is equal to 0 for every t, then certainly if we pick 3 values of t, for example, at t equals 0, it must be 0, so you have C1 plus C2 plus C3 equals 0. At t equals 1, it's also 0. And you get CE plus CE inverse plus C3 equals 0. And at, say, t equals minus 1. So we've just picked three values of t. We know, let's suppose that this is 0 for every t, then certainly it's 0 for these 3 values of t. So this is CE inverse plus CE plus, C1, 2 and 3. Okay, so we have a system of 3 homogeneous equations. It's a homogeneous 3 by 3 system, and by now we know how to solve this. So we're asking, so if there is if we can show that C1, C2, C3 here necessarily must be 0, then we're done. So let's work out what the set of solutions of this homogeneous system is. So we write down the augmented matrix. This is 1, 1, 1, E, 1 over E, 1, 1 over E, E, 1. So that's our augmented matrix. And if we try to transform this into row echelon form. So to get the first row, we do 2 row operations to get the first column into row echelon form. And I won't write down what the row operations are, so it should be clear what they are. And what happens to the other 2 rows? Here you get 1 over E minus E, and this is going to be 0 here, and then here is 1 minus E, and 2 minus E minus 1 over E. Okay, so it should be clear what the row operations are to get this. So if you notice that the matrix that we obtain, so this part here, it's clear that this is invertible. So we can do 2 more row operations here and reduce it to a matrix where the diagonal entries are all 1. I mean, here the diagonal entries are all non-zero, so it has determinant is non-zero. And this means that the determinant of the original matrix is non-zero. And so it's invertible. it follows that it's invertible. And so there are no free variables here, no free variables. And so the unique solution is C1 equals C2 equals C3 equals 0. So unique solution is C1 equals C2 equals C3 equals 0. So in particular, this equation here, we can see that if this is 0 for every t, it must be 0 for t equals 0, t equals 1, and t equals minus 1, and then that implies that C1 equals C2 equals C3 equals 0. So in particular, the three functions are linearly independent. So the set of, so the set of functions is linearly independent. Okay, there is an alternative way. An alternative method is the following. Let's say an alternative method is the following. Okay, suppose that we have functions f1, f2, up to say fn, and we want to show that these are linearly independent. Suppose that f1, so suppose that these have sufficiently many derivatives. Sufficiently many derivatives. So consider. So what are we trying to do? We want to say that if this is C2 F2 plus. So we want to say if this is equal to 0 for every t, then C1 up to Cn is equal to 0, and that's the definition of being linearly independent. So we're interested in whether this is linearly independent or not. And if you can find a set of functions, a set of numbers C1 up to Cn, not all 0, such that this is identically 0, then we say that these are linearly dependent. So let's suppose that. Let's consider this equation. If this equation is 0 for every t, then its derivatives must also be 0. So in particular, we have C1 f1 prime plus C2 f2 prime plus Cn fn prime is equal to 0. And you can carry on taking as many derivatives as you want. So let's go on up to the n minus first derivative. So n minus 1, this is the n minus first derivative. Okay, so if the first equation here is 0 for every t, then all of these equations must be 0. And in particular, this is a homogeneous set of equations. So this is equivalent. This can be written as this f1 prime up to fn f. Sorry, let me just correct that. This is f2 up to fn f1 prime f2 prime up to fn prime, and then so on up to f1 to the n minus 1 f2. So these are the derivatives, higher derivatives, fn minus 1. So the above set of equations is precisely this homogeneous system. And of course we know that this will have a non-trivial solution precisely when the determinant of this matrix here, so when the determinant of this matrix here is equal to 0, then this will have a non-trivial solution. If the determinant of this matrix is non-zero, then the only solution will be C1 up to Cn equals 0. So let's write a definition. Let's write, we define W f1 up to fn is a function of t to be the determinant of this matrix above, so it's f1 t. Let me not write all the time. This is fn t, and this f1 prime t, fm prime t, up to f1 to the n minus 1, fn n minus 1 t. Okay, so this is the determinant of this matrix. We call this the Wronskian. Or rather, we call it the Wronskian of the functions. And we have the following results. If the Wronskian of f1, f2 up to fn, so this is a function of, it's a function, and if this is different from 0, for at least 1, in I, then the functions f1, f2 up to fn, this set of functions is a linearly independent set of functions. Linearly independent on our interval I. Okay, so we only need it to be different from 0 for 1. It may be different from 0 on the whole of I, but that's not what we're asking. Not what we're asking. We're just asking if it will be different be different from 0 for at least 1 t. And if that's the case, then these functions will be linearly independent on I. It's simply, if you consider this equation here, so then if the determinant of this is non-zero for some t, so for them, then these C1 up to Cn necessarily have to all be 0. So that's all. Okay. So this you can check on the example we did, and using the Wronskian also. Okay, but I won't do that. And there is an example in the lecture notes using the Wronskian to check that a set of functions is linearly independent. So let me state the following. So in the following section, we will want to consider families of vector-valued functions. And in this case, we want to talk about linear independence of vector-valued functions. So we have the obvious definitions. So the natural definition is the following. So we say that the functions, so these are vector-valued functions now, x1 t up to say xn t, where x, say xi t, so this is it's a vector valued function, so this is x say I, write it like this is x 1i t up to x, let's call it m. Okay, m may equal n, or it may not, it doesn't matter here. So these are vector valued functions. We say that these are linearly independent. On an open interval. I, if this equation, if whenever this sum is equal to 0 for every t, this implies that all the c's are 0, so c1 is equal to up to cn is equal to 0. Okay, so let's suppose that typically we're going to assume that m is equal to n. Let's suppose that m equals n. And consider let's consider what the equation we're interested in. This is c1x1 t plus up to cn xn t. We're interested in when this is 0 for every t. This equation, we can rewrite this as this is c1 x1, this is x11 up to x n1, and cn x1n up to xnn. Okay, and this is the 0 vector. Okay, so we see that this is just, we can write this out as a matrix equation. This is a x11, xn1t, xnnt times c1 up to cn is 0. And we know that this is, so if the determinant of this matrix here is non-zero, then the only solution is the trivial solution. Okay, so we define let's say definition. So we define the Wronskian of these functions. This is the determinant of the matrix here. This is x11 t equal to x1n t, xn1 t up to xnn t. So this is, I mean, this is. There should be a determinant. Sorry. This is determinant. This is the determinant of the, when you take these as a column vectors, this is x1 and x2 and so on, up to xn, right? It's the determinant of this matrix, and we call this the Wronskian of these functions x1 up to xn. And we have the result, that theorem, it's easy to see. So if the Wronskian of x1 up to xn t is never zero, is non-zero rather, for some t, then x1 up to xn, so this set of functions is linearly independent. Okay, I should say this result and the result before, you should be careful to not read too much into it. So here, if this is non-zero for some t, then these functions are linearly independent. If it's identically zero for all t, then we can't draw any conclusion. And the similar statement for the previous theorem about the Wronskian. So when the Wronskian is non-zero for at least one t, then we're happy, we can state that the functions, or the vector valued functions in this case, are linearly independent. Okay, so now I wish to go on to basic theory of systems of first order linear ODEs. Okay, we're going to start off by considering the case of homogeneous ODEs. So let's consider homogeneous case. Okay, so we're going to start off with a homogeneous case, and this is the case where you consider this. Okay, so this is the homogeneous. This is a homogeneous system of first order linear ODEs. And the basic result regarding these is the following. It's the superposition principle. The principle of superposition. And it states the following. So let's refer back to this equation, we'll give it a number. Suppose that x1 and x2 are solutions of equation 1. So then the function c1 x1, so this linear combination, plus c2 x2 is a solution of 1 for every for all c1 and c2. So c1 and c2 are just numbers here. So for numbers c1 and c2, this linear combination is a solution. So the proof of this is easy. I'll leave it as an exercise. Okay, so this is a superposition principle, and this is what makes the whole thing work. For homogeneous systems of linear ordinary differential equations, they satisfy the superposition principle. And okay, so we know that linear combinations, in particular linear combinations of solutions, are again a solution. So the question arises, can we find a small set of solutions such that the linear combinations of those solutions gives all solutions. Okay, so small set, by that we mean a minimal set, so we want the smallest set. Can we find a smallest set of solutions such that every other solution is a linear combination of those solutions? And minimality, we'll see, it means that the set should be linearly independent. That should be clear. So we want to find a linearly independent set of solutions such that every other solution is a linear combination of those solutions. Can we always do that? Okay, so let's continue considering equation 1, and let's add an initial condition. Let's consider the initial value problem. So we consider the same equation, dx dt is equal to atx and x at t0. So pick some point t0 is equal to let's put it 0, 0, 1, 0, up to 0. So where this 1 is in the ith place, okay. By the existence and uniqueness theorem, this is a system of linear first order differential equations. It has a unique solution for any initial condition. So we know this has it has a unique solution. Let's let xit, let's let xit be the unique solution. Okay, so we in this way we get n solutions of our equation. So here, so we suppose that at is an n by n matrix valued function. N by n matrix valued function. Okay, so we will get n solutions in this way, and what we claim is that these n solutions are linearly independent. So the set of vector valued functions x1 t up to x n t is linearly independent. Okay, so when we talk about a linearly independent set of functions, we mean over a certain domain. Here we mean over the whole of the real line. So how do you check this? Well, as we discussed earlier, to check that a set of vector valued functions is linearly independent, the simplest thing to do is just look at its Wronskian. So its Wronskian is the following. Xn at t, so this is the determinant of x. So we take these functions, and so here I'll write it just like this. So this is x1 t x n t. So now we think of this as a vector. So this is so here this is meant to be an n by n matrix. So we write x1 as the first column and x2 as the second column and so on. So this is an n by n matrix. And so these are the columns, this is the first column and so on. Okay, so this is the Wronskian of these, and so I should say, let's evaluate at, so if you notice here, I picked a value t0, so t0 is some point that I picked. Let's evaluate this at t0. T0. So this is the determinant. So x1 at t0, this is 1, 0, 0, and so on. And the next one is like this. And you go all up to this. So you can see that this is just the identity matrix, and its determinant is 1. This is in fact never 0. I mean, this doesn't depend on t at all. This is non-zero, and so the functions are linearly independent. So this is a linearly independent set. Okay. Okay. So now we claim. Now let's return to our original equation. So so here's the following theorem. So every solution of equation 1 is of the form for C1 x1 plus I'm going to put the t here. So it's of this form for some C1 up to Cn for a unique, in fact, for a unique choice C1 up to Cn. Okay, so here, what's going on? So here we've, let me just remind you, so we've picked a point t0 and x1 up to xn are defined as above. Okay, so they're defined as this is the unique solution of this IVP. So it's a unique solution of the IVP given here. Okay. Okay, so those are solutions of our equation, and we're saying that every solution is a linear combination of those solutions in a unique way, in fact. Let's prove this. So let's let x t be an arbitrary solution. Arbitrary solution of our homogeneous equation. So let's let x at the value of t0. So this is a vector. So let's write this as say k1 up to kn. It's just a vector. Now consider y t, so this is a vector valued function which is equal to k1 of x upper 1. This is a function, these are all functions of t. Kn x upper n t. Okay, so by the superposition principle, y is a solution of 1. So then y is a solution of 1. By the superposition principle. Position principle. And y at t0, if you just check this, because x1 at t0 is 1, 0, 0, 0, so, and so on, so it's clear that this is k1 up to kn, so it's exactly the same as x at t0. Okay, so we see that x and y both satisfy the same initial value problem. This is same as x at t0. So x and y are both solutions of an initial value problem, hence they must be the same by the existence and uniqueness theorem. So by the existence and uniqueness theorem. Theorem xt equals yt for all t, which equals c1 x1 cn xn for all t. Okay, so xt and yt satisfy the same initial value problem. They satisfy the same equation, and at t0 they have the same value. So they must agree. Okay, so every solution certainly is a linear combination of x1 up to xn. How do we check that c1 up to cn are unique? So for uniqueness, suppose that x is equal to c1 x1 plus cn xn and xt can also be written in a different way. So cn prime xn. Okay, let's suppose it can be written in two different ways. Then, if you subtract, you get 0. So this is 0 vector is equal to c1 minus c1 prime x1 cn minus cn prime xn. And so c1 up to c. So by okay. So now we know that x1 up to xn are linearly independent. So hence these the only way that this linear combination can be 0 is if c1 minus c1 prime is equal to 0, and cn up to minus cn prime is 0, i.e. So by linear independence. Independence. Up to cn equals cn prime. Okay, so that's the end of the proof. So that's all there was. I think I made a slight typo here. Let me just correct that. So yt was k's. So these should be k's rather. So these are k1 up to kn, of course, here. Okay. Okay, so we know that given an arbitrary homogeneous system of linear first order ODEs, we know that we can find a set of solutions which is linearly independent, and the linear combinations of this set give all solutions. Okay, so that's what we've established. Such a set, such a linearly independent set, which generates all solutions, we call it a basis. So a linearly independent set let's call this B of solutions of our equation 1, such that every solution of 1 is a linear combination of solutions from B. We call this a basis. Or a fundamental set. Of the space of solutions, or for the space of solutions. Okay. So that's a basis for the space of solutions. This what we've said is that every solution of our equation is a linear combination of these. In fact, there's a name for all for what we're doing here. So what we're saying is that the space of solutions is a vector space, and this is a basis for that vector space. So these are concepts from linear algebra, and in fact from linear algebra we have the following. So in fact, we're saying that this is a finite dimensional vector space. So what do we know about finite dimensional vector spaces? So I'll say the following two things that will follow. So any two bases let's say B and B prime of the space of solutions of our equation have the same number of elements. So we know this from linear algebra. So if you recall your linear algebra, if you've done some, if you have a finite dimensional vector space, then any two bases of it have the same number of elements. So here, our space of solutions is a finite dimensional vector space. We have found one solution, one basis containing n elements, so every other basis must contain elements. So in particular, if AT is an n by n matrix, or n by n matrix value function, then every basis for the space of solutions, of the space of solutions, will have n elements. Okay, the second fact is that any linearly independent set, containing n solutions is a basis. Okay, so to find a basis, it's sufficient to find a set of n linearly independent solutions. And this is from linear algebra. If you have a vector space which is n dimensional, then if you pick any n linearly independent vectors in that vector space, they will necessarily be a basis. Okay, so if we find n solutions which are linearly independent, we know we've found a basis, and that means that every other solution is a linear combination of those solutions. Okay, so this was all general theory. So now let's restrict ourselves to considering, I mean, in the general case, it's not so clear how to find actual solutions. So we're interested in actually finding solutions. So this was just, okay, the existence and uniqueness theorem tells us solutions exist, but it doesn't tell us what those solutions are. So how do we find solutions? So let's restrict ourselves to constant coefficient systems. So for these, we will be able to explicitly describe a basis for the space of solutions. So we want to consider the equation x or dx by dt. I mean, sometimes we write this as x prime. Let's write it as dx dt equals ax. So here A is independent of t. So A is a constant matrix. So A is an n by n matrix. An n by n matrix. So it's independent of t. Okay. We want to. So basically, the general theory tells us that if we find n linearly independent solutions, then this will be a basis for the space of solutions. So how do we find solutions? So if we think of, by analogy, the case where n is equal to 1, so solutions there are exponential functions. So what do we expect here? So we will look for solutions of the form x t is equal to v e to the lambda t. So here v is a vector, lambda is a number. Okay, so so here this is sort of, we're trying to generalize the case where n equals 1, so the scalar case. So when n equals 1, the solutions are exponential functions. So, and all solutions are just constant multiples of exponential functions. So here we look at, say, vector multiples, of exponential functions, and let's see if we can find solutions of this form. Okay, so so this is a solution of our equation. So let's call our equation 2. So so for this to be a solution of 2, we need, so what do we need? So what is the derivative of x here? So this is, as we said, we can differentiate vector valued functions. Just you differentiate them entry by entry. So here, in this case, this v is constant, and you just differentiate this, so you get lambda times this. And for this to be a solution, we want this to be equal to a times x. X here is v e to the lambda t, so it's a v e to the lambda t. So we need lambda v e to the lambda t is equal to a v e to the lambda t. So now e to the lambda t, this is always non-zero. So we can divide out both sides. We can divide this out from both sides. So we get, let's switch sides. So av is equal to lambda v. And we recognize this. This is our eigenvector, eigenvalue equation. This is our eigenvalue, eigenvector equation. Okay, so what do we see? We see that so if lambda is an eigenvalue and v a corresponding eigenvector, of A, then xt is equal to v e to the lambda t will be a solution of our equation. Okay, so we can find some solutions like this. Providing we can find eigenvalues and eigenvectors, we can find some solutions of our equation. So let's look at some examples. So sometimes this is enough to, will be enough to actually find the set of all solutions of our equation, as we'll see. Okay, so so here's a homogeneous system of first order linear ODEs. So let's write this as we write this as x1 prime x2 prime is equal to 2 1 1 2 x1 x2. So this is our matrix A. Okay, so it's a constant coefficient matrix, and we can look for solutions by looking for eigenvalues and eigenvectors of A. Okay, so let's look at the eigenvalue. So eigenvalues of A are given by solving this equation. Okay, and this equation is 2 minus lambda squared minus 1 equals 0. And this factorizes. So we can write this as 3 minus lambda 1 minus lambda equals 0. Okay, so we have two eigenvalues. So we have lambda 1 equals 3 and lambda 2 equals 1 are eigenvalues. And as we saw before, let's pick one of these. And we can look at this set of all eigenvectors. So we do exactly as we did before. We solve. So we should look at, we want A minus lambda 1I times V equals 0. And this corresponds to this equation. So this is the augmented matrix of this equation, and by some raw operations. So I won't describe the raw operations here. You can do them yourself, and you can check what the solution should be. So we get you get V is equal to K times 1 1. So this is the set of all solutions. Gives this gives all eigenvectors. All eigenvectors. Okay, to find a solution, we just need one eigenvector. So x t. So let's put k equals 1 and our V to be this, e to the lambda, here lambda is 3. 3t is a solution of our equation. This equation here, so this equation, we might call it 3. Okay. Okay, if I choose a different k, we get a multiple of this, and this is obviously another solution by the superposition principle. Okay, so we might as well put k equals 1. So that's one solution, and so if you take the other value of lambda, so lambda 2 equals 1, and now work out the eigenvectors. In this case, you get so I won't write it down, I'll just tell you the answer, k minus 1, 1. So this gives eigenvectors. So k is non-zero, gives all eigenvectors. So let me call the previous one x1, and so you get here, so x2. Again, let's put k equals 1, so minus 1, 1. And here's lambda is 1, so it's e to the t. It's another solution. Here's another solution of our equation. Okay, so now are these solutions linearly independent? So x1 and x2 are linearly independent. Let's look at their Wronskian. So Wronskian of x1 and x2. So this is the determinant of, so x1, recall this is 1, 1, e to the 3t, so this is e to the 3t, e to the 3t, and x2 is minus 1, 1, e to the t, so this is minus e to the t, e to the t. And if you check the determinant of that, so here we get e to the 4t plus e to the 4t. So you get 2e to the 4t. And that is never 0 for any t. Non-zero for all t maybe. So in particular, x1 and x2 are linearly independent. Okay, this is A is 2 by 2. We know it has a basis of two linearly independent solutions. x1 and x2 are linearly independent solutions. And so C1, x1 was here e to the 3t, 1, 1 e to the 3t plus C2 minus 1, 1 e to the t. So this gives all solutions. Okay, varying C1 and C2. So when you put C2 equals 0, C1 equals 1, it gives you x1. And if you put C1 equals 0, C2 equals 1, it gives you x2. And for letting C1 and C2 vary, you get every single solution like this. Okay, so that's an example of a 2 by 2 system. You can do this for bigger systems. So here's another one. Let's solve the system. Minus 1, 1, 2, 1, 2, 2, 3 works. Okay, so 3 by 3 system. And so last time we saw that here this has 3 eigenvalues. You have So lambda 1 equals 1, and we found that the eigenvectors correspond to some multiple of this, and we had, so eigenvalues are 1, 2, and 3, and the corresponding eigenvectors, I'm just describing them here, 1, 1, 0, and okay, and so we get x1 is equal to v. So put k equals 1, so you get 0, minus 2, 1, e to the t, x2, e to the 2t, and x3 is equal to 2, 2, 1, e to the 3t. So these are three solutions, and they're Wronskian. So here you get e. Let me try again. So you get 0, minus 2, e to the t, e to the t, e to the 2t, e to the 2t, 0, and 2 e to the 3t, 2 e to the 3t, e to the 3t. And when you compute the determinant of this, not do this, you get 2e to the 6t, and this is never 0. So the x1, x2, and x3 are linearly independent. We know that the basis should consist of three linearly independent solutions. So, in particular, x1, x2, x3 is a basis for the space of solutions. Hence, all solutions are of the form C1 times x1 plus C2 times x2 plus C3 times x3. Okay, so this gives you the case for this gives you a 3 by 3 case. Let's say something in general now. So let's suppose that, now consider, so suppose, let's say, now consider, again, the system x prime equals ax, where A is an n by n matrix. So let's consider what can happen. So suppose that A has n linearly independent eigenvectors. Let's say v1 up to vn. Just write it like this. And corresponding to the eigenvalues say lambda 1 up to lambda n. So these may not all be distinct, which may not all be distinct. So lambda 1 may equal lambda 3 or so on. I mean, some can be repeated, which may not V distinct. It doesn't matter. So then we have x1 is equal to v1 e to the lambda 1 t, xn equals vn e to the lambda n t. So these are solutions of our equation. So let me refer to this equation as, I guess, 4. Let's call this our solutions of our equation 4. And moreover, they're linearly independent. If you check their Wronskian, by checking their Wronskian, they are linearly independent. Wronskian, they are linearly independent. Hence, they give a basis. They form a basis for the space of all solutions. So x is equal to c1 v1 e to the lambda 1t. The sum up to vn e to the lambda nt. This gives all solutions. So every solution is given like this. Okay, so the question is, can we always find, does every matrix have, every n by n matrix have n linearly independent eigenvectors? And the answer is no. So, so not all n by n matrices have n linearly independent eigenvectors. So this is certainly not true. I mean, e.g., if you consider the matrix A equals 2, 1, 0, 2, you can check easily here. This matrix, you can find it has one eigenvector, but you can't find two linearly independent eigenvectors of this matrix. Does not have two linearly independent eigenvectors. You can check that. Okay. So when do matrices have n linearly independent eigenvectors? Here's a situation where they do. So if an n by n matrix has n distinct eigenvalues, lambda 1, lambda 2 up to lambda n. So distinct means that each lambda I is distinct from each other lambda j. So lambda I is not equal to lambda j if I is not equal to j. So then the corresponding eigenvectors. So corresponding to each eigenvalue, there is at least one eigenvector. So pick a non-zero eigenvector for each eigenvalue, then the corresponding eigenvectors will be linearly independent. Okay, I won't give you a proof here. There is a proof in the notes. So this is an important case. When you have n distinct eigenvalues, so this is the situation that we've considered in our example so far. Each of them had n distinct eigenvalue, and they had n distinct eigenvalues. So the eigenvectors we found were linearly independent, and from that we found a basis for the space of solutions. Let me just note here that this is just a sufficient condition. It's certainly by no means necessary. Note that if a matrix may have less than n distinct eigenvalues but still have n linearly independent eigenvectors. Note that even if a matrix, let's say n by n matrix has less than n distinct eigenvalues, it may still have n linearly independent eigenvectors. So e.g., just take A is, say, K times the identity matrix, for example. K can be arbitrary. K is just anything. So this matrix, it has just one eigenvalue, K, but you can find two linearly independent eigenvectors, certainly. So, okay, right, I'll stop here.